Welcome back. We're still working on example 8.1.7. That's in the section about infinitely many optimal solutions. We had a company that was trying to build two different types of kayaks and was trying to figure out how many of each to build to maximize their profit. In the first video, we set up the linear programming problem and we started with the initial tableau of the simplex method. In the second video, we found two different optimal solutions. We found this one, 8 and 14, and then by pivoting on a column with a 0 in the profit row, we got a second optimal solution. That second optimal solution is right here, 16 and 8. Both have a profit of 8,000, so the company could do either and end up with 8,000 of profit for that week. All right, so in this video, we'll answer the next two questions. So we're going to place both optimal solution in the following sketch of the allowable region to try to figure out what's going on. All right, so the first optimal solution, that was 8, 14. So 8 and 14 is right here. And then after pivoting, we had a second one. We'd found 16 and 8 right here, 16 and 8. 16 and 8 would be this point. All right, and we're told to sketch the line P equals 8,000. Well, this point gives us P equals 8,000. This point gives us P equals 8,000. And P equals 8,000. P was, actually, let's go look. P was 300x plus 400y. So P is 300x plus 400y. So that's a line. And the line contains these two. So it's going to contain the whole, this entire line is P equals 8,000. All right, so a lot of these points are not in the allowable region, but if you notice, a bunch of them are. So everything right here in this segment, that's an allowable region. All right, so we're asked in part 4 to say how many optimal solution does this problem have and give all of them. Well, anything on that line would work. So the whole segment between our two optimal solution, 8, 14 and 16, 8 would be optimal. All right, so geometrically, that's what's going on. The level curves for the optimization function, for the objective function, they're parallel to one side. And so it wouldn't intersect at just one of the vertices. It would intersect at an entire segment. And so we need to find a way of writing that entire segment. So let's take x, y. I'm going to get a line. So I'm going to start at 8, 14. So that's A. And then I want to add the vector AB. AB is the vector 8 minus 6. So plus T 8 minus 6. I don't want to include all values of T because most of the line is not in the allowable region. So I wanted just to start here, which is really a T equals 0, and end here, which is a T equals 1. So I'm going to take this for T in 0, 1. Another way, another way of thinking about this is to write 8, 14 plus T times B minus A, so 16, 8 minus 814. And then I could bring the 814s together. So I'm going to get 1 times 814 minus t times 814 plus t times 16, 8. And so I'm getting 1 minus t, 814 plus t, 16, 8, and again 4t in 0, 1. All right, so this is a nice way of putting it because it's easier to generalize to many dimensions. I have two things that add up to 1. So I'll phrase it even that way. It's going to be a multiple of 814 plus a multiple of 16, 8. And I need to make sure that s and t are in 0, 1, and that s plus t is 1.